University for the software engineering domain. My group will tackle multiclass respiratory disease detection system using deep learning on acoustics. So we are basically working with three respiratory diseases, that is COPD, COVID-19, and TB. Yeah, so this is basically my content the presentation. So I'm going to look at the CNN model, the architecture diagram, then I walk through. Then I'll also look at the architecture strengths, limitations, and the baseline role. And model 2, I will be looking at the LSTM model and this architecture diagram and this walkthrough. So we have COPD, COVID-19, and TB. These present it's normally difficult to find differences between their symptoms. So because these present themselves with similar cough symptoms, so delayed diagnosis tends to lead to disease progression and community spread. So I'll move to the role to my first model, that is convolutional neural network, in short form CNN. So CNN's role in this project is acting as our baseline model, and CNN basically does the acoustic feature. We extract the spatial patterns in the acoustic features. So it tends to answer the question of how much diagnostic information do we have. Yeah, so why the convolutional layers for the acoustic features? In that the neighboring features tend to carry out related information. So you may see that the MFCC1 and the MFCC are adjacent frequency bands. So bands, the spectrocentroid and the bandwidth tend to describe the same spectrum. So a ConV1 filter exploits this neighborhood structure very well. So that's why we went for the CNN. And of course, now in our model, you're going to see that we are going to take 36 input features per recording, per audio recording. So in these 36 features, we are going to have 13 MFCC means and then 13 MFCC standard deviations, the spectrocentroid, bandwidth, the rho of the ZCR, and the R mean. So at the end of the day, we are going to have an output of probability score for each of the 4 classes. That is COVID, COPD, TB, and then the health one. So all these will give a probability that will sum up to 1. So this is my CNN architecture diagram. With here, I have the input. So this input is taking in the 36 features from the audio that have been extracted from the audio recording. Then moving to that, the architecture, we have a block 1, a convolutional block 1 that bears 64 filters with a kernel size of 3. So meaning the features will slide across. We shall slide across 3. We shall slide across 3 features, and we will be able to detect the patterns within this audio. So the purpose of this block is to basically detect the local acoustic patterns from the recording. Basically, we shall see patterns like a high MFCC1 mean plus a high RMS may result into a loud frequency band, which can loud frequency band cough. So which for example may mean COPD. So at this block, we shall also do badge normalization. That that stabilizes the training. We shall also do a max pooling. Max pooling tends to halves the sequencing, like that's halving of the sequencing. That halving of the sequencing like helps to retain. It tends to retain. It tends to retain the strongest signals. Yeah. Then there's also after that there's also a dropout of 0.3, meaning 30%. So this dropout tends to avoid the overfitting. So moving away from block one, you go towards the block two. Block two now bears 128 filters. Yeah, so this increase in the number of filters is from the fact that block two is not dealing with raw features from the audios, but rather dealing with the output from the block one. So it works on this output and makes several combinations. And from the output of block one, you'll find that we shall have multiple combinations that have been made. So retaining the same number of filters is not applicable here. That's why we tend to double the number of filters at this point. Yeah, so then from there we go to the flatten and dense. So at the flatten basically converts, it collapses a 2D, feature and maps it into a one single D vector. So this bridges convolution, convolution and classification. Then the dense combines. The dense is going to combine. It combines all the detected combinations as at the block two. So combines all of the detected combinations into simultaneous patterns. So at this dense layer, we have a dropout of 0.4 because there are high risks of what? Of overfitting at this point. That's why we tend to increase the dropout percentage. Yeah, so this layer, that's what is done at this layer. Then from here, we shall go at the dense for Softimax. So at the dense part for the Softimax, we are going to have 4 neurons. So and each of these 4 neurons is corresponding to what? To one class. And at this class, we are outputting a probability summing up to 1. So you may find that maybe if COPD is taking up 68%, then the other will take up 19%, then TB may take up also another percentage. So here it should sum up to 1. That is what I had for the architecture diagram. Then when we come to so this is basically taking you through that architecture as I have explained. Then when we come to how the model performed, so I trained the model several times, and my greatest accuracy has still go down, but I have an accuracy of 0.773. So this is a model accuracy of 77%. So from my classification report, you see that the CNN performs excellently for COPD and TB, and tends to struggle with COVID-19 and health part. So here you can see that for a classic pattern of a spatial pattern for this classic model that is for spatial pattern only, you find that it tends to do well for it masters classes with the number of distinct acoustic features. So COPD and the TB have several distinct acoustic features. So that's why the model performs well on this. Then we looking at this, COPD, we have a precision of 1, then a recall of 1, then an F1 score. So this is a perfect This is a perfect what score for that. Then you see that TP we have a near perfect score where we're having 0.987, 0.96, and then this. Then we're having CNN's weakest score at the COVID-19 part. Then we have CNN's worst performance at the health part. Yes, so that is how the model performed. Then I'll straight I'll straight away head to the second model, that is the CNN LSTM model. So this basically extends CNN by adding special memory here. It adds the LSTM layer that acts as special memory, in that it is not going to keep forgetting the features. It has mastered to keep track of these features. So it basically captures how acoustic features related to each other across the vector. So I'll take you through the architecture diagram for LSTM. So we are having an input here, the audio input bearing the 36 acoustic features, that is the MFCC spectros, the ZCR, and the RMS. So this is our input. So from here we head into a CNN layers where we still of course have the block one bearing 64 filters to detect the acoustic patterns from the audio recordings. Then we shall do, of course, a max pooling at this block one, and also still after the max pooling, we shall still do dropout and then to avoid overfitting. Yeah. Then from there, we shall head to the second block, still under CNN layers, where we have an increased number of filters to 128, because this is dealing with an output from this and that doing the combination. Yeah. So from this part of the CNN layers, we head into the LSTM layers, of course, of this CNN LSTM model. So you see that at the LSTM layers, we are going to read the CNN output as a sequence, and we are going to do position by position to obtain some hidden state. So in this LSTM, there's 3 gates where we have the forget gate, what the model is discarding. Then we also have the input gate, what the model is storing, and then the output gate, what the model is passing forward. So you see that the final hidden state is compression, of course a compression memory. Yeah. So it basically has so this, after it going through here, it is passed to this other classification where we're having a dense of 64, and then we shall do a dropout for that. So at the end of it all, it is outputting, of course, also the 64, there are 4 neurons bearing they are corresponding to each class, and these of course will also have a probability summing up to, and so we also see we also come here and see that the scores we had an accuracy of 0.7162, so this is an approximately 72%. So you see that it has yeah, it is still is doing well on COPD, TB, and still also struggling with COVID-19 and the hereditary. Yeah. So with this score still accurate, it's a perfect score for COPD and also a nice score for TB, but with COVID-19 and the hereditary side, there's also still a struggle here. So yeah, so thank you to me. I let's just stop at this point.